Hey folks, this is the first lesson in the Waves and Sound unit, and in this lesson we're going to be focusing just on some basics of waves to give us a framework and context for understanding how sound and other sorts of waves work. So three main goals for this lesson. First, talk about what a wave actually is and compare two different types of waves, which are called longitudinal and transverse. Our second goal is to look at the wave speed equation and how we can use that to solve problems that involve wavelength and frequency. And then our last goal will be to look at different behaviors and interactions of waves that end up getting some pretty cool results. All right, so let's dive right in. Now, first of all, a wave is basically some sort of disturbance that causes energy to be transferred from one place to another. Now, it's really important to notice that matter itself is not transferred or moved by a wave. It's just energy that's moving through the matter that we're able to see. So, for example, when you see water waves coming to shore, it's not a matter of those water molecules way out in the middle of the ocean have moved all the way up to the sandy beaches that you're hanging out at. It's just the energy moving through the water, but the individual water molecules are just bobbing up and down. Okay, so when we see a wave, it's really just energy moving through it, not actual particles moving. One way to help me think of this is when I think of being at like a baseball or football game and the fans do the wave. So you see that signal move all around the stadium. It's not that there are actual people running all the way around the stadium with the wave. It's just the energy that they're passing along from one person to the next. It's the exact same in water waves, in light waves, in sound waves, etc. It's just energy being transferred along, not actual matter. All right. Now, whatever it is that the wave travels through, we call a medium. Now, there are two basic types of waves that we can classify: waves that require a medium and waves that don't require a medium. Now, waves that require a medium, require some sort of matter to travel through, are called mechanical waves. The water waves I talked about, those are mechanical. Sound waves require a medium. It's true that in space no one can hear you scream because there's no matter for that energy to travel through. Seismic waves, earthquakes, also again require some sort of medium to travel through. The main wave that we can think of that doesn't require a medium is light, which is a good thing for us because if light couldn't travel through a vacuum, then the light from the sun couldn't get to us and it would be cold and dark and, very not life-sustaining here on Earth. Okay. So that's the basics of a wave. Now we'll talk about two different types of waves that we can focus on. Now, one type of wave is a transverse wave. Now, this is sort of your standard sine wave that you've probably looked at in math at some point or another. And the key idea here is that the particles oscillate perpendicular to the direction that the wave is traveling in. So, for example, we see this wave here. We can imagine that it's traveling up and down, up and down, up and down, but all the while it's moving to the right. Okay, now the oscillations that we see are going up and down, which is perpendicular to the overall direction of the wave, which is directed to the right. That's how we know that this is a transverse wave, because of that perpendicular orientation of the oscillation and the direction of the wave. Now, it's easier to point out some things in wave anatomy using transverse waves, so I'll take this opportunity to show you a few features of a wave. Whatever the height of what we call a crest or a hill, you could sort of think of it as. That height is called the amplitude. Okay, that's measured from the midpoint up to the very highest point here. As I mentioned, the top point is called the crest. The very lowest part is called the trough. And then if we measure the distance from one crest over to the next, or from one trough over to the next, we call that the wavelength. It's represented by this funny Greek letter called lambda. My guess is that for a lot of you this is review. That's okay, it doesn't hurt to hear it again. Examples of transverse waves: light is probably our favorite transverse wave, but then also certainly water waves are also an example of transverse waves as well. Now, this is sort of the classic standard wave that we think of, but there's another one as well, and it's called longitudinal. Now, the difference here is that in a longitudinal wave, the particles oscillate parallel to the wave direction. Okay, so whereas before, if we wanted to send a wave along this way, we would see the oscillations go up and down, up and down, up and down. But here we can almost imagine taking a slinky and like pushing it forward and back, so that it sort of makes this zigzaggy motion, forward, back, etc., etc., etc. Okay. Now, in places along this wave where our particles are really bundled together closely, we call those compressions. We can see everything really tightly coiled at points A, C, and E. Those are points of compression. And in the parts where things are really spread out, we call that a rarefaction. So that's points B, D, and F. We can see that the particles are not very dense at all there. So we call that a rarefaction. Examples of longitudinal waves are sound, and seismic waves are also typically longitudinal. Now, to help us envision this a little bit better, we turn to the ever wonderful YouTube. Okay, now what you're going to see is we've got two slinkies. One's going to show a transverse wave, and one's going to show a longitudinal. Now, this is short, so you'll want to pay attention. Okay, so see how the transverse, it goes up and down, whereas longitudinal goes back and forth. Okay, so there's the difference. Now, another key feature of waves is that they are cyclical. We see the same pattern repeating over and over in a wave. Now, because waves are cyclical, we can point out a couple other key features of waves. First is the period, which is represented in an equation by a capital T. And the period represents the amount of time it takes for a wave to complete one full cycle. So from crest to crest, for example, or from compression to compression. So just the amount of time it takes for it to get to one point and then get back to that same point again in the next cycle. We tend to measure this in terms of seconds. And then we can think of a period as the number of seconds per cycle, if that's helpful. Okay. Now, another corollary to this then is the frequency. And frequency is kind of similar to period, but sort of flipped on its head. With frequency, we're looking at the number of cycles per second. Okay, so whereas period was the length of time for one cycle, frequency is the number of cycles we can fit in to 1 second of time. Now, we measure frequency in a unit called hertz, which is just a cycle per second, basically. Now, since these are sort of the flip-flop of each other, it works out that way mathematically as well. So they're reciprocals of each other, meaning that the period is 1 over the frequency and vice versa. Okay. Now, waves, again, are transferring energy from one point to another, and anytime we've got things moving, one of the questions we tend to ask is, well, how fast is that energy moving? Now, I've mentioned a few different parameters that define how waves move. We've got wavelength, frequency, the amplitude, the medium that they're traveling through. The question is, what actually matters in terms of determining the speed that a wave travels at? And it may interest you to know, or it may not, but I don't really care, I'm going to tell you anyway, that medium is the only thing that affects the speed of a wave. Okay, so changing the wavelength of a wave doesn't change how quickly it moves. The frequency doesn't change how quickly it moves. Amplitude, no change. The only way we can get a wave to move faster or slower is by changing what type of matter it's traveling through. Okay. Now, the reason for this that we'll find out is that wavelength and frequency, people tend to think if we increase that, we'll get the wave to move faster. But wavelength and frequency have this weird relationship where if we get a longer wavelength, the frequency naturally decreases. Or if we increase the frequency, the wavelength naturally decreases. So the two are always canceling each other out, which is why changing wavelength or frequency doesn't end up affecting the speed of the wave. If we make a longer wave, then what happens is we just get fewer cycles in per second, so it doesn't do us any good. Okay. Now, using that, we can actually calculate the speed of a wave in a given medium using the wave speed equation, okay, which states that the speed of a wave in meters per second is just equal to the frequency times the wavelength in meters. Again, this kind of emphasizes that if frequency goes up, the wavelength goes down, and that causes us to have one constant speed for a wave for a given medium, which is why, for example, the speed of light we always say is 3 times 10 to the 8th meters per second. It just doesn't matter what the wavelength or frequency is, it's always going to be moving that fast through a vacuum. Granted, it'll be a little slower in air or in water or what have you, but we're not going to worry too much about that right now. Okay, so we can determine the speed of a wave, which is going to be a constant for a given medium, by multiplying the frequency times the wavelength. All right. Now, on to our last goal, and this is where things get kind of sexy and fun, okay? We've got 4 different interesting, unusual interactions that happen when 2 waves interact with each other that are really unique to waves, things that we don't see happening with matter interacting with itself. So these are kind of fun. Now, the first interaction is reflection. Now, this is one that I'm sure you're very familiar with. It's the idea that a wave can bounce back after hitting a boundary, which doesn't really work quite as well for us. I mean, I guess we kind of bounce off of things if we hit them hard enough, but waves, it's much easier. They bounce and they just keep on moving again. Okay. Now, I've got a little simulation to show you. We've got this string along here that we can send a wave pulse down, and we've got a boundary here on the right hand side, so we're going to send it from the left over to the right, and we're going to see how it reflects. Now, I'm going to start off with a fixed end, so the idea is the particles right here at the boundary can't really move. They're sort of stuck in place. So if we send a pulse down to that fixed end, okay, what you should notice is see how it reflects back, but it switches sides. Okay, there it goes and switches sides. Okay, so when a wave reflects off of a fixed end, it continues along, but it flips over onto the other side, which is kind of unusual. If we change that boundary to be a loose end, so now what we see is that this particle is free to oscillate up and down along this pole. Instead, now what happens when it bounces off of this loose end is it reflects on the same side. So kind of a cute, weird little feature of waves reflecting off of different boundaries. So there's our first one, reflection. Second interesting interaction is interference. Now, to understand interference, I'm going to throw out 2 terms for you. First, superposition is this idea that waves can overlap with each other and occupy the same space at the same time. So like when we've got 2 waves in the same place, we can just kind of add them together. And that's totally allowed because waves are energy, not matter, and we get to do totally different things with them. Now, because superposition exists and waves can overlap each other, we get something called interference when we have multiple waves occupying the same space at the same time. Now, obviously, this doesn't work for matter because if I'm sitting in this chair, you cannot also be sitting in this chair unless you're sitting on top of me. But you and I cannot occupy the same space at the same time. But with waves, it's different. They can overlap. And as a result, we can then add them together, basically, giving us 2 different sorts of interference, constructive and destructive interference. So if we have 2 waves that are both perfectly aligned, they've got crests at the same place, they've got troughs at the same place, we get constructive interference where those 2 waves add up, creating an even bigger amplitude wave, right? Which is why, for example, if you get 2 speakers going, the sound is louder, depending on where you are, than it would have been with just 1 speaker because you're hearing both of those waves and they're constructively interfering, giving you a louder sound. Now, what you might have noticed on occasion is that there are certain quiet spots in auditoriums or theaters, or even just in your room if you've got a nice stereo system. And that's because in addition to constructive interference, we can also get destructive interference. Now notice over here on the right, we still have 2 waves that are overlapping each other, but in this situation where one wave has a crest, the other one has a trough, and vice versa. And what that ends up doing is that they end up canceling each other out to give you no wave at all. And this is the science behind those quiet spots. Those are places where the waves are destructively interfering and essentially canceling each other out so that you can't hear that sound wave anymore. third interesting interaction is called refraction, which you may have noticed if you've ever drunk anything out of a straw, which I'm assuming most of you have. What you might notice is that there's this weird thing where it looks like the straw gets like cut in half and moves over somewhere along the way there. And that's because light waves refract. When they travel from one medium over to another, they will actually bend because one side slows down faster than the other side slows down. This is also why if you've ever like had a goldfish in one of those clear bowls or tanks, you know, like you can see it from one angle at the side and it looks really enormous, but then if you look at it from above, it just looks like a normal goldfish. It's because when you're looking at it from the side, the light is bending outwards basically so that your fish looks much bigger than it actually is. So that explains some of the weird effects that we get sometimes when we're trying to look into something in water or in glass, for example. We'll get that light bending and kind of skewing and distorting the shape of whatever object is in there. Okay. Now, our fourth interaction is called diffraction, not to be confused with refraction. So refraction was the bending of light as it changes from one medium to another. Diffraction is the bending of a wave, could be light or could be something else as well, when it passes by some sort of obstruction or obstacle that's kind of causing it to have to move out of the way. Okay, so we can see here that we've got just waves passing through just in a straight line, but then once they hit these boundaries here, they kind of bend around it, creating this more, you know, rounded, almost circular sort of shape to them. Okay, we can see this again in an actual ripple tank. So here we see just water waves, and we've got a light shining through on the other side, and we can see those water waves bending around the walls. Now what's really cool is that we can actually see this happening with light as it passes through a very small opening, and this I totally did not know existed until a few minutes ago. It turns out the opening in your phone's camera lens is very, very small as well, so we can actually see a really cool diffraction pattern just using an iPhone camera. Okay, see that diffraction pattern right there where we're getting this constructive and destructive interference due to those waves bending and kind of reworking themselves around? Very, very freaky. Again, could not happen with actual matter. You and I do not change shape as we go around doorways, thank goodness. But with waves we can. Kind of weird. All right. Now, one other thing that then arises from all these different interactions is we can get something called standing waves. So basically, if we have waves traveling through a closed medium and we get the exact right wavelength, the exact right frequency, we can get the reflections to work out perfectly to form standing waves, so that there are certain places called nodes where the waves are always destructively interfering, and other places called antinodes where the waves are always constructively interfering, so that we get these waves that seem to just oscillate in place. Okay. Now just to show you this one more time, we actually have standing waves in a pool right here. By oscillating one side of the pool at the exact right frequency, we get these crazy standing waves so that they just seem to be oscillating in place. Now what's actually happening is this side right here is actually moving back and forth and sending wave pulses down to the other side, which is reflecting them backwards. But the way that those end up interfering with each other, it just looks like a wave just standing in place. Very freaky, right? So again, in order to make that standing wave, we basically have to manipulate our wave and find the exact right wavelength or the exact right frequency such that we can get a node at each end of our boundary. Now I know that was kind of a lot to take in, and we'll be talking more about standing waves in a little bit when we talk about harmonics and how musical instruments work. That's all I have for you right now. Have a wonderful rest of your day.